Swayam Prabha. Digital India. Educated India.
Okay, now let's try to prove B implies C. This is a bit involved, but let's see if we can argue this. What we want now is, suppose we assume this B, then I want to show that for any tau, n tau is Poisson distributed with rate tau lambda, and further the conditional joint distribution of my count times is expressed in this format. Okay. So now let's first focus on what does this event mean. So given tau, n tau equals to n means by the time tau n counts have happened, right? That means n tau equals to n means exactly n count might have happened before time t, and n plus 1th count should have happened after tau. Then that is when I am going to call n tau equals to n, right? So that is what I am writing here. So that means, like, if I am going to look at my n of this random variable t1 all the way up to tn plus 1, it should be such that if you are going to look at the realization, t1, t2 all the way up to tn should, that is the times of these counts, should have happened before or at least by the time tau including tau, and the t plus 1th count time should have happened after tau. This happens, when this happens, that is what you are going to call n tau equals to n, right? If this t plus n has happened before tau, that means n plus count is already happened before time tau, right? So that is why I have to express this completely, I also have to include this tn plus 1. Suppose I just say this and leave it like this, it is not clear that this is going to capture this, because I have not told you whether the tn plus 1th count has happened before tau or not. If that has happened before tau, then this is not correct. So for this to make sure, I have to explicitly say that the n plus 1th count happened after tau. Okay. Now let's try to find out the conditional . So how I am going to obtain this? I want to find conditional PDF of this set of random variables given n tau equals to n. So how I am going to leverage already the things that I know? I know that if you just forget the conditional part, the joint distribution of this n random variables, I have already computed it, right. I have this distribution, okay. But now I have this conditioning here. What does this conditioning will imply to me? So because of this conditioning, if you go back and recall our conditional density property, because of this conditional link, I will get an extra term which divides this PDF here. This probability is the one which divides over. So let me make that clear here. So if I want to So I am just trying to use the definition of my conditional probability that we have defined earlier. So because of this conditioning, this extra probability is showing up here in the denominator. Now if you just apply this definition here, what I will have is, this is nothing but lambda to the power, now n is going to be replaced by what? In this formula, if I have to use that formula here, I have to replace n with n plus 1, and then what? E to the power lambda times Tn is going to be replaced by Tn plus 1, right, because I am looking at Tn plus 1 here, and then this term is there. And this is for the case where my T1 is greater than equals to T2 and is Tn, and then this is equals to tau, and this is equals to Tn plus 1 here, and this is going to be 0 otherwise. Yeah, see that when I adapted this formula from here to this case, that ordering, earlier the ordering did not include any tau here, right, it was just T1, T2 all the way up to Tn arranged in strictly increasing order. But now that I have this tau factor here, so this joint PDF is defined on this T's such that these T's are strictly increasing, and such that this Tn plus 1 is strictly larger than tau. That is where I could use the PDF in this format, okay. This is because I have to ensure that I have been conditioned on the fact that there are n counts till time tau. Okay, now, so we are there, like we wanted to define this distribution, conditional distribution, we have this conditional distribution, but the only thing that has thrown extra is we have ended up with this Tn plus 1 variable here. But whereas what we wanted to show did not include Tn plus 1, right, it was only talking about joint distribution of n random variable here. Now how to derive, so I have this joint distribution which is now of n plus 1 random variables. Now if I want to get a joint distribution of only in the first n variables here, how to get that? So just integrate this function over what? Tn plus 1, and what is the possible values of Tn plus 1? Tau to infinity, right, it could be any value. So if you just do that integration, what you will end up is, So if you just do this integration T1, T2 all the way up to Tn given n tau equals to n. So after doing this integration what you will end up is e to the power lambda lambda to the power n is there anyway, and then we will have lambda power tau divided by probability that n tau is equals to n. This is for all 0 T1 T2 all the way up to Tn, and this is less than or equals to tau, and this is going to be 0 otherwise. So I have just integrated this function between tau to infinity. If you just write like I am just ended up with this function. So now if you just look into this function, does this function depends on any of these variables here? Earlier when I have this function, at least it depended on the variable Tn plus 1 which was my argument, but now after doing this integrating out, it is only lambda to the power e to the power lambda t tau, and the denominator also is only my conditioned n tau equals to n. Now what is this? I have a distribution, I have a PDF, and this is a constant, a PDF which takes only constant value. It should then what this is? It should be kind of uniform distribution, right? Like I have ended up with a distribution which is uniform, and if it's a uniform distribution, and also we know that a PDF should be such that if you integrate it over its region, it should end up what? It should indicate what? So if that's the case, and if it's a uniform distribution or it takes a constant value throughout, what should be the value of that CDF itself at every point? That function itself. So okay, so let me rephrase it. So if I have a PDF which is independent of my argument, that means at every point it is going to take the same value, right? Like for example in this case, you give me any point, it is going to take the same value. Further, if I am going to integrate this over the entire region, it should equals to 1. That means necessarily that at every point this function is nothing but the reciprocal of its area, right? Then only if I am going to integrate, and if it is constant, then I will end up with a 1 value. So in that case, this value should, whatever I got here, should be reciprocal of the area of the region where this ordering holds. You understand this? So let's imagine for a 2-dimensional case. I am letting tau, each one of these to go up to, so I have this T1, I have this tau, and this is I am only letting it go till tau, because both T1 and T2 are random variables which can take at most value tau, right? Now what is the region here where T1 is going to be greater than T2? So let's say I draw a 45-degree line. In all of this region, T1 will be greater than T2 or T2 will be greater than T1? T2 is going to be greater than right. If I am going to fix this, and if I go all the way up, T1 will always, so I have this region, right. So I am just, let us focus on this. So if you just focus on this, what is the area of this entire area? Tau square. And now what is the range where this ordering, okay, in this case I am interested in T1 less than T2, right. So this, and I mean I can ignore this part because that line itself do not have any area. The case where T1 equals to T2, I will, what is the area of this region? That is going to be exactly half, right, of T square by 2. In that case it is going to be tau square by 2. So similarly, if you extend it to n dimension, the area where this ordering holds, if I am going to tested, what that will be, any guess? Tau raised to n divided by n factorial. Why that should be? Huh? That is the result. Okay. Fine, let us take it as result. Okay. So then what you expect this value to be equal to? 1 by that quantity, right, tau to the power n divided by. So we expect this to be equals to, reciprocal of that is n factorial t to the power 10. Okay, and you see that that is what I have already mentioned here. But this is just like one step of this, right, like I have to show that for each tau this is a Poisson random variable. What I have just showed is this conditional distribution satisfies conditioned on this n tau equals to n is going to be this n factorial by tau to the power n. Now how to show this? That for every tau greater than 1, n tau is a Poisson with rate lambda t. Whatever this relation I have you, if I go ahead and manipulate it, I am going to get probability that tau n tau equals to n is equals to what? Lambda n tau n e to the power lambda t lambda tau divided by n factorial. So what is this? So what is this the random variable then, n tau? So I am saying that the probability that this random variable n tau takes value n is expressed in terms of this, but now what this looks similar to, or what this exactly is? Poisson with what? So n tau is Poisson. So I could just write this as lambda tau to the power n and e to the power lambda tau divided by n square, right. So this is my rate, and this is Poisson with rate lambda tau, and that is exactly our claim here. So in a way what this third point, C point, is telling us, the Poisson process can also be thought of like an uniform random variables, a collection of independent uniform random variables where that n points occurs can be thought of like they are going to happen uniformly in the interval tau, that is each points I am going to draw, that is going to happen uniformly with parameter tau, but I have also this constraint that these points need not be arbitrary, they have to be in increasing order, right. So that is tau t1 has to greater than t2 like this. So because of this I have end up with this n factorial term here. Okay, now quickly argue why, if this is true, this implies that my process is Poisson. Okay, so now what I need to show, if I am going to assume the C property, I need to show that all the 3 properties of the, if I assume that some process is such that it is going to satisfy all, it is satisfies point C, then I have to show that this also satisfies, this implies 3 properties of my Poisson process. Okay. Now let's try to say C equals to A. Suppose I am given this, let us say T1, T2 and up to Tk. I am given this K variables and also this n numbers, n1, n2 all the way up to nk, and then let us say I am going to define n to be n1 plus n2 plus all the way up to nk. So think of this, I have been given as the time count times T1, T2 all the way up to Tk. Now I am going to define, and also imagine that this n1, n2, nk are nothing but the number of items you want to put in the interval 0 to T1 is n1, and that between T1 to T2 as n2, like this. So I have total n items here, n1, which is the sum of all these items. Now I am going to define some Pi here. Pi is going to be defined as Ti minus 1 divided by Tk. So what is this? Suppose I have, let us say T1 here, T2 here, and T3 is bigger and T4 is smaller, and I have some T5 here, and this is like starting 0. So P1 is going to be proportional to this interval, P2 is going to be proportional to this interval, and P3 is going to be proportional to this, like this. So notice that Tk is constant, that is the total length. Let us say this is Tk. So this is Tk, and now for every Pi I am just going to take the length of the interval. So I have basically defined probability Pi that is proportional to the length of the intervals. Pi I will just define now. So I have just I will say where I am going to use it. Like Pi is, I have defined to be a number which is defined like this. You can think this as like a probability term here. So if you just add it over all i's, it is going to add up to 1, right, between 1 to k here. You have to convince yourself, like if I am going to assume this C holds, and I think that, just let me write this. So by C, I am assuming C holds, right. By C, the distribution of, so what we are saying is, if because of this uniform distribution as a interpretation we have from this C point, we can assume that if we are going to define this Pi's to be probabilities proportional to the interval n, and if I have n numbers, let us say, given to me, and if I throw this n items on this interval, probability that it falls in this interval is going to be proportional to the length of this interval. Okay. So that is what we are going to now use. So the distribution, the number of counts in each interval is as if each of the n counts thrown into the subinterval at random falling into the ith interval is going to be pi. So now, so if we say that we have n items and ni items are going to fall in the ith interval, so what is this probability is going to be? Like if I have n objects and I throw them, n1 of them go into the first interval, n2 of them go into the second interval, and nk of them go into the kth interval. What is that probability is going to be? Like I am choosing each one of the object independently and I am just throwing. Every time I throw, the probability that it is going to fall in the ith interval is pi, which is independent of the other. So then what is the probability that ni counts go into the ith interval is? It is going to be p1 into n1, p2 into n2 into pk into nk. So this is for a given n1, n2 all the way up to nk, right? But when I have n total counts, in how many ways I can partition them into n1, n2 all the way up to nk such that their sum is equals to n? I have a multinomial distributions, right, in this. So the number of ways such that ni counts in the ith interval is simply n choose n1, n2 all the way up to nk, which is defined as n factorial divided by n1 factorial, n2 factorial all the way up to nk factorial, right. So I have n things, I am indifferent like where the count is happening, I am just like throwing them, right, like I am just interested in what how many of them go into the ith interval, and then I am just looking at the probabilities in this fashion. So for a given n1, n2 like this is the probability, but right now I do not know how this n total n gets split across this, right. So I have this multinomial distribution. Now finally how to exploit this now? Now I have this. So suppose let us say nti minus nti minus 1 is equals to ni. Let us say for all I equals to 1 to n. So let us compute this probability. I want to compute that, okay, in the interval between t1 and let us say ti and ti plus 1, or between ti and ti minus 1. So this should be I minus 1, there are ni objects, okay. This you can write it as nti ntk equals to n total number of objects and probability that nti minus nti minus 1 equals to ni between I to n and k, given condition that n tk equals to n. Now coming back to the C third property again here, from the third property, that point C here, we already know that this distribution is what? Probability that nt equals to n. This is a Poisson distributed with rate lambda tk, right? That is the length of the interval here. So this is going to be lambda tk, and how many counts till then? There are n counts, e to the power lambda tk divided by n factorial. And what is this? So I am basically asking, there are ni counts between in this interval, and there are n such intervals, right? So how I am going to do? I am first going to look for a possible realization, and then when I know the possible realization, I have, this is the probability associated with that. So I will consider it over all such possibilities, right? From there are these many ways of choosing, these many ways of partitioning this n into n, n1, n2 all the way up to nk. When I have this kind of partition, what is the associated probability? The associated probability is p1 to the power n1, p to the power nk, and all the way up to p to the power k nk. So if you just replace this guy by its n factorial divided by n1, n2 all the way up to nk factorial, and further if you replace each of the probabilities as we defined earlier in terms of their intervals, that is, you will just replace this pi by what? Ti minus 1 divided by tk. If you just replace, what we are going to get, t equals to I k equals to 1, sorry, I equals to 1 to k. Then, so you just verify that. I am just directly writing this. Okay, so what is this now? I am finally able to express this probability here as the product of k probability, k terms here. What is each term here? If you just focus, let us take one particular I here. I is ranging from 1 to k, right? Let us take one particular k. So if you just look into that, what is this is going to be? So that is going to be a Poisson with rate lambda ti minus 1. That is a lambda, that is a random variable with Poisson distributed with rate, and this is nothing but the probability that that random variable taking what value? Ni value, and that is exactly this value, right, for particular I. But now what I have able to write it as, it is now able to write it as all this as a product of all these k values. So that means what we have done is, this probability is nothing but so these are like increments, right? I am able to express these increments as the product probabilities. Each probability term here corresponds to a Poisson random variable. So that means I am already showing that the third property of the Poisson process, that this independent increment, so each of this random variable corresponds to a Poisson random variable with rate which is going to be proportional to the length of the interval. Further, we have shown that through this product that these increments are independent, because each one of them I am able to write it as a product fashion, right. So, is it clear that like by expressing this I have been able to show both second and third properties, that is independent increments and that each of these random variable is Poisson distributed with the rate corresponding to lambda times the length of the intervals. And the first property, that counting process, that is obvious, right, like we are doing a counting and you can just verify the definition of counting process on this. So, with this we are able to show that C implies the three properties of a Poisson process. So, hence C also implies, if C holds, then it is clear that my process is a Poisson process. So, any of this characterization you can check, and that all implies the same Poisson process. So, okay, let us stop here. If you have any doubts on this, you can ask now.